So next we're going on to, okay, now we need something that's a little bit more custom, something we have to actually make. So in order to implement diffusion terms for ions and electrons, we'll need the kernel objects to represent, and to represent that diffusion term, and that includes that diffusivity coefficient you saw earlier, but just includes that extra diffusivity coefficient. So again, for now, we're going to ignore the boundary term. So we have a no flux boundary condition there effectively. So the volume integral looks exactly like the diffusion equation multiplied by that constant. So I have to write as much code. But before we do that, we do need to talk about a few aspects of Moose, and I'll take the opportunity now to do that. So for really complicated geometries at INL, we generally use Qubit. I do not use Qubit. I use a software program called Gmesh, which is free. I believe Qubit does have a license. It can work as long as they can output a file that libmesh reads. So it's a pretty extensive number of files. Move this mouse out of the way. So, and it can be extended. So we've had people in the past that have come to us and said, we'd like to use this very specific file, and Moose can be extended.
So can we make a survey and understand what people use for the meshing? Because, for example, in my group, we use a lot Gmesh, but this might not be the case for others. So what are you guys using in general for mesh generation?
Anyone got a preferred mesh generator that they use?
No?
None? Is that the answer? Or? So yeah, I don't use finite element software usually, so that's why I don't use any.
Yeah, but you need a mesh in any, even if you're using finite volumes or finite.
Yeah. Usually structured grids. So they're
Okay.
type structured grids.
So I use a high frequency structure simulator, which is a commercially available software, which kind of generates.
Anybody else?
I've been using like a fluid that you can generate mesh, and if there is a way, say you can have a solid file, that I build the geometry, and the geometry just go to a software, and then you can generate mesh. Then fluid can make a mesh dot mesh, so that
STL or IGES typically. But then there is the problem of converting the geometry into a mesh, right?
Yeah.
That's a target.
Okay.
Yeah.
Just curious. Okay, thank you.
So the first one that we've seen already is that generated mesh type. So that's built in to Moose. It can do lines, rectangles, and prisms, but it could be extended to do more shapes. So for 1D, left is 0 and right's 1, and it changes based on 2D and 3D. But then you can say left, or you can say 0 in an input file, and Moose will be able to understand what you're trying to do, what boundary you're trying to get to. So then you can specify all of the different parameters for your mesh. For if you have a very specific geometry and you say you have an interface for water or something like that, you can give that a human readable name, and Moose will be able to understand that in the file. Then this refers to Qubit. Files can have numbers or names associated with them, and they can be assigned on the fly. So one thing that I don't think we go into, okay, we do. So here we have an illustration for a mesh. We're pulling a 3 different material mesh out of an Exodus mesh file. And then we're saying that we're assigning block IDs assigning block IDs and then translating those to a name, wood, steel, and copper. And again, we're taking the boundary IDs in the file and giving them, or to you later if you haven't run a particular simulation in a while. So I'm not as familiar with the displaced mesh program, but that has been used in the crystal plasticity modeling, I believe, is where it's in contact. Okay. So when your materials, so your material interface is deformation in the displaced form, and then as you view your output, you can see the mesh deform. Let's see. Okay. So just like all the other parts of Moose, the output system is designed to be modular. So you can make multiple objects in your console, what information you'd like to get out. Maybe you have an Exodus file, but you only want that data to be output at the end of your time step rather than at the beginning, or you could even say, well, I only want you to put out to Exodus when the simulation fails. And so if you want to see what was occurring when the simulation fails, you can do that. Okay, so as I was saying, you have different execute on parameters to tailor how things are output to your screen or to a file, sometimes to troubleshoot an issue or to get a specific insight about what's happening in your simulation. So then this will actually, like it says here, if you use this flag when you're running your input file, you can enable output in the first place. Now the default is there when you're enabling the Exodus block. I usually always say Exodus equals true, but if you leave Exodus, if you leave it blank, what's still output, what's still default to a particular file? So, okay, so you have to fill in the outputs block. So porting settings and the default settings for that file. Another version of this would be, say I want to output to CSV, I could say CSV equals true, and it would be a default configuration for a CSV output. Okay, so again, this is a summary again of all of the different options you have to output information. So I'm not as familiar with the advanced output settings, but a little bit more insight about what's going on in your solve, and in order for troubleshooting or whatever your needs may be in this case. Okay. So again, executing on and being able to dictate what file name you see. So if you have a specific file name that you want all your output to be, you can name it, and Moose will follow that convention. So in this case, you have an output block where you're saying, well, I want an output, an Exodus file with a standard output name, which is just input_out, say. But then and it takes the first part of this from the actual use your interval, and then say every other one. And then the use of this name disables any other setting you have for a file base name. So sometimes if you think you didn't set this, or you can't find your output file, sometimes it's because you forgot to change that and you thought you did. Okay, so this is a summary, and I'm not going to go through every single line of this, but this is a summary of, if you decide you want to look at this later in a more full format, please post to the workshop group or ask us, any of us, and we can try to help you with that. Okay. So the Moose, so we've done Cartesian coordinates up to this point, but Moose also supports axisymmetric coordinate systems. So in your problem block where you're saying your FE problem is coordinate type RZ, and you're telling Moose what's the axis for.
So what about spherical?
Yeah, spherical is always, and so right here where it's spherical. Oh, another question. Yeah.
What happens if your preferred coordinate system is cylindrical, but there is no symmetry? There's structure in the azimuth direction.
Well,
You will get a solution, but if it's the wrong one.
yes, like a gut check or like a quick and dirty simulation. So in your case, so say you would have a geometry that's relatively symmetric, but may have some differences about it. In that case, you would want to generate your own mesh with those geometries in there, or I've done some simulations that could be axis symmetric, but then because of as opposed to doing an axis symmetric solve. So in that case, I would never rely on the generated mesh system if you had if you had situations like that where the generated mesh system would not be able to cover, unless you're just trying to get an idea of what something's going to be. Like you can get it close enough and move on from there. But for situations where you have a pretty uniform structure, then obviously stick with this unless you need to. So does that answer your question?
Yes.
Okay.
So which softwares do you use to generate your own mesh?
So
for asymmetric?
well, so I use Gmesh, and then so Gmesh allows me to write a file, an input. It's also visual too. So obviously I'm most experienced with that particular tool, but it's not unlike any other mesh generation tool where you have a visual aspect to it in 3D. So that's generally what I do. Does anybody else have any? Okay, yeah.
For a 3D coordinate system,
Mhm.
is say cylindrical, but is not axis-metric.
Okay. Yeah. So you can do so you can have a 3D. In that case, so it's not axisymmetric. So would you be using, David? Would you be using like a Cartesian there? Yeah. So you wouldn't be using, or you wouldn't necessarily be using the spherical, but I guess you could. You probably still could. You just wouldn't be telling it. You wouldn't be telling it where it's. You wouldn't be giving it a symmetrical.
Whenever you write your origin in Cartesian and you are rewriting that into a symmetrical form, there is this term that's like inflating your integral so that it's the right one, and that's what that thing is doing. So if you tell most that your program is symmetrical, you're saying that you're solving the symmetrical EDE. But if it is not symmetrical, I'm wrong integral.
David, I guess that the question is, can we plug a metric tensor inside a Cartesian reference frame so that we have some deformation of the coordinates along a preferential direction? So that we use x, y, z as a main solver for the Jacobians and everything, the Gaussian integrals, but we have some metric tensor that accounts
Yes,
for.
absolutely. Yeah, you can do that. Yes.
So
Yeah.
the answer, I guess, is yes, and never accounts for, in this case, a cylindrical deformation, but it can be generally general.
Is anybody else? Go ahead.
That's mainly related to your your PDE. So
Mhm.
your tensors are special. You can obviously put that in because you have the control.
So every object in Moose inherits from a central location, Moose object. So every object you create has a very similar structure, template structure. So I'm going to show you some pseudocode essentially with the close to being right structure, but just not. It's not. These parts of your header file you're not going to change. So you're defining you have your class label, another label for your class, and then what you're essentially inheriting from. So in this case, we're inheriting from some base class with the name myObject. So your class myObject is inheriting from base class. You have its constructor, and then what you're see virtual. You would be overriding the computing your residual contribution. So you'd have virtual compute QP residual and then override, because you're overriding it from the base and giving it some sort of definition. In this case, you're saying you have an inherited method. You could also be adding your own functions to this as well, but you have this. So for your C code, the way you register new kernels in Moose is via this register Moose object function here. So in this case, say our app is called animal app, and so we have animal app and then the name of your object. Then you have this valid parameters block that you have the valid parameters from your base class or from whatever your inheritance dot, and then a function to add a parameter or add a coupled variable or something like that. Then this location in your code, you're taking your parameters, which are provided by your user in your input file, and then they are brought in to your object to be used in your inherited method. So for example, you could have a parameter here in your parameter space. It gets pulled into your code. Your object may know here to what you've given it a name, and it's pulling whatever material definition is by that name, and then used. So it's not everything here or here is going to be things that you see out in your input file, but the basic idea is like this is where your used parameters are gonna live and get defined. So okay, so every object, like to control all aspects of your particular object, while leaving the code unchanged, so you don't have to go beyond what you see in front of you. So if you have a valid parameters function here, so we have valid parameters of kernel, that's we're inheriting convection, we're inheriting from kernel. And so then we're saying, let's add a required parameter input file. So if I had a kernel that was type convection, one of my parameters would be velocity, and then I would have to give it a vector. Now, in my input file, if I didn't give it a vector, if I didn't give this parameter a vector, then it would complain. So it's checking that type that you've defined it as. Now, parameters, and this will probably come up soon, but I'll go ahead and say it, these descriptions. And so that can be helpful for if you're looking at things visually, what this actual kernel does, or what its parameters are. And then you have your coefficient that you're adding. So the difference between required param and param, required param, if you don't provide it, you'll get an error. Moose will refuse to run until you provide it. But adding a parameter, Moose will, if you don't provide it, Moose, whether it be 0 or whatever it is, I usually try to give it a default there. But the required parameters don't have that. Okay, so the document, I'm not going to spend a lot of time on this because I think a lot of parts of the documentation system are in the process of changing. But those descriptions and the Moose, you can generate documentation of your code based on how you've structured it, which can be a pretty useful tool, especially if you don't want to make quite as much documentation later yourself. But like I said, I'm not going to spend a lot of time on this just because some of this stuff is changing. So you can reference this later. And one thing that you can do, dump. It'll dump all the registered objects for that what can exist in your input file to give you an idea of what exists in your code. Okay. This is just going over some types. Again, like you have your required param and param and various structures that based on what type you use. And again, this more relates to Peacock, but it's to make it a little bit more context aware of what's actually going on. There are a considerable number of names for these, and so if you want a complete list, you can see that in the header file Moose types. Okay, so the default parameters, like I said, you can provide a default. So in this case, you have defaults for any coupled variable, post-processor, or function, and or you can use the parser. The Moose parser will take these parameters. You can define a parameter over a range, and it'll check this. In this case, it'll check whether it's inside of the range you specified. But the parser will understand what you're doing there. And so if you want, okay. So I don't know a lot about the nuts and bolts of this, but I use it in my code to check for different states, or different cases in my code, so. Okay. So again, this is more related to Moose and Oom. So you'll define your component where you have your possible options here, and in this case, you haven't supplied a default. So you add a required parameter of your component that'll read information, and the Moose would complain if you don't select one of these options. Okay. Then, so David, do you know more about this function or multi-Moose and Oom? I've never used this functionality, and this could also be a reference slide, but.
So if you want to provide these schemas, then let's go then output system, and let's say you want to output on initial condition or every time step, beginning, time step end, final, and let's say fail. That's an example of multi-mousse enum.
Okay.
Because all these.
Okay, thank you. All right. So, like we've been saying the whole time, a kernel is a piece of physics. So it can represent one or more operators. In this case, we've kind of separated it up term by term. But if you have a collection of terms that are pretty much always together, or you want to group them as such, you don't have to go term by term if you don't want to. You can represent your residual defaults to the Jacobian free method we talked about earlier. You don't have to override these if you don't want to calculate them. So then they have access to your current value of your variable and the gradient of your variable. Then these are the trial functions. So what your interpolation functions are for your variable. The test function that you're multiplying your node that you're at node location in terms of the indices. A quadrature. So the quadrature Q point here gives your XYZ coordinates. Quadrature point gives your quadrature point, and then your element, and then you have other aspects, but that's what's available to kernel principally. So now, we're back to which this is what we boundary condition terms, which you define from here, and then your Jacobian for this is you're taking the derivative of this with respect to u sub j, and pulling back out the gradient of your test function, the gradient of your basis function. And so if you turn that into Mousse code, then you would have this diffusion inheriting from kernel. We have this registered under our name Mousse app and diffusion. And so we don't have any params here, but there is an optional param for adding a class description for your documentation, which you may want to take advantage of. And so then we have our grad u times grad test, as we expect to see, and then grad phi j and grad test. And again, before you can ever use a Mousse object, you must register it, and registration's just a one-line function call at the beginning of your C file. Okay, so now we're on to the meat of the step. We're going to take the diffusion object that we had, and we're going to extend it. So we have our header. We are saying that we're defining the various aspects of our object, but then again, this is templated. And so then we have, we're going to override the residual, and we're going to override the Jacobian. And so this is our addition. So we'll be setting this from the input file, our diffusivity, our constant. And so when we get to the C file, we'll have the add required parameter diffusivity. I'm not going to give it a description for the documentation or for Peacock if we want to. And so now we're taking the diffusivity that we've pulled in from the input file, getting that parameter, and setting that equal to our internal diffusivity value that we defined back in the header file here. And so then we have diffusivity, and because we've inherited from diffusion, we know that hasn't changed, and the same for the Jacobian. Okay, so with our input file here, this is essentially the same from earlier. In this case, I've changed the name of the variable now, where we have a sum population density, and we have our kernel here, and we have a diffusivity, a constant of 64.29. And we've defined our Dirichlet conditions, so we have 1E4 U standard executioner block. Still using hyper and boomerang ng because of the type of problem it is, and then we're just outputting to a simple Exodus file. Okay, and so in this case, I'm going to run this again, and so get a chance to experience more pair view, if you wish. So let's run this. Or if you don't wish, either way. I've gotten a lot of questions. Okay, so let's clear this out. And we're going to go to, go back to the tutorial application. I'm going to go to test. So again, We're going to run this. I'm going to run this and give it the input file step2.i. As that runs really fast, and we have a pretty good looking residual there, pretty small. And so I'm going to go ahead and say, let's look and see what this bad. And I'm going to try to make it a little bit smaller so it fits in on the stream. Okay. Okay, and then I just screwed it up, of course. So let's go back to, okay. So everyone, if you want to follow along with me, and let me know if things are getting kind of wonky, if the tutorial app isn't running, but try to run this just to get more practice at running a test or a case, and then looking at the results. For peer review in particular, practice makes perfect, and for Moose, being able to look at results and understand what you're seeing also, practice makes perfect. And if you have any questions, and so we can see our variable here, we're going to enable that. So I have a setting up here on peer review turned on to automatically apply whatever changes I make here. Otherwise, you'd have to click and then click apply before things might show up on your screen, so remember that. I forgot to mention that earlier, so that's really important if you don't have that setting enabled. And so now we have our slightly different shape because we've added that coefficient to it. And we have slightly different imp files, but slightly different slope. But anyway, so that's what we expect, so that's good. And so, you know, after this, we would create a simple test that mimics that behavior and give it whatever name that we needed to. So in this case, in the first test, that wasn't necessarily something you needed to do because we didn't create any new code. But whenever you create any new code, you want to make sure you create a test for it, just so you don't break it later accidentally. Okay. Okay. So if you wanted to create your own application, which we're getting ready in a little bit to do a hand look at the results and see how close you got. So in order to do that, you'll want to create an application. Of course, you could use the tutorial app if you wanted to do this, but in normal cases, you wouldn't have your own tutorial app to look at. So you would want to run the stork.sh script in that directory inside of Moose. So you would navigate to the projects directory of your app, put it there, and then the script will automatically create the directory structure that you need for a basic Moose app. And every Moose app comes with a simple diffusion test that you can run, and if that doesn't succeed, then you've got some bigger problems underneath the hood with Moose. So that's why they give you at least one test. I think initially it was animals native to Idaho because Idaho National Laboratory is developing the framework, but you can name it whatever you need to. And again, if you run this script inside of Moose, it won't allow you to do it. So make sure you run it from the projects directory. Okay. So this is kind of a stopping point. Let's see, what time is it? 11:30. And then we'll have the results. I'll throw up the results and we'll see how close everybody got. But that'll take some time. And so I wanted to it might be worth it to head to lunch for a little bit. But before we go, I wanted to see if there were any questions before we move on to this hands-on portion. Okay. Well, then I think we're going to activity, and so everybody can kind of get a feel for creating this stuff and not just hearing me talk at you and telling you how it's structured. So with that,